about structures. And in general chemistry and in biochem, we always followed rules like honk 1, 2, 3, 4, hydrogen forms 1 bond, oxygen forms 2, nitrogen forms 3, carbon 4, and we also followed the octet rule. Those were ways to guide you when you were beginning to draw those dot structures so you could figure out how to draw them. Honk doesn't necessarily work. I do use honk sometimes, and when I have a molecule that follows honk, I'm like, it's good. But sometimes you're not going to be able to follow that. So don't worry if you break honk. And with the octet rule, a lot of things can break octet. So, looking at here, let's talk about octet rule was saying that every atom likes to be surrounded by 8 electrons. That's why we saw that ionic compounds, metals, tend to lose valence electrons to get down to a full shell. So like this beryllium, well, let's say magnesium will lose 2 valence electrons. So it has 10 electrons, just like neon. Neon is a full 8. Things like chlorine has 7 valence electrons. It gains 1 electron to be like argon, having a full octet. These are all stable amounts of electrons, but in order to make molecules sometimes, because these bonds are stable, sometimes you will break the octet rule, and the time you are allowed to, there's a few, I didn't mention this one, but boron is satisfied with 6 electrons around it. It can have up to 8, but it's satisfied with 6. The other thing is silicon is your first non-metal on the third energy level. So I've got metal, 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 then I've got silicon. So it's the first non-metal, or metalloid. It's the first thing that undergoes covalent bonding. Silicon and larger can access the d orbitals, because remember we said these are the 3d. They're on the same energy level as the electrons are that are bonding here. So silicon and larger can have more bonds than just 4 bonds. They can have more electrons than just 8 electrons surrounding them, because they can use their d orbitals in bonding if they need to. So don't, if you see something like carbon breaking the octet rule, you know you have a problem, or something like fluorine has to follow the octet rule. Silicon and larger, if it breaks the octet rule, don't worry. Just make sure you use the right number of electrons, you counted up everything's valence electrons, and that you followed the octet rule as much as you could. So, for the most part, we draw simple molecules that just have a center atom and then a bunch of things surrounding them. For the most part, that's AP Chem. There's going to be some organic type stuff, but this is where we're focusing on those dots right now. You draw the center atom and try to figure out how many bonds it's going to make. This nitrogen is going to make 3 bonds with the hydrogens. This fluorine is going to make, or sulfur is going to make 2 with the fluorine. The sulfur will make 4 with the fluorine. Xenon making 4 bonds. That's weird, but now I know I can break the octet rule. Rarely happens, but it can. This iodine, it's going to be in the middle of 2 other iodines, so it can make 2, it's going to be making 2 bonds. So I can kind of just see how many bonds I have to make by looking at the formula. So first I draw my central atom, nitrogen. Nitrogen is smaller than silicon. It's on the 2nd energy level. It's not going to violate the octet rule. So for this one, I just say, well, nitrogen, looking on the periodic table, let's go back and look at it. If I look at nitrogen, nitrogen is here. It has 1, 2, 3, 4, 5 valence electrons, and hydrogen has 1 valence electron. So that means I have 5 valence electrons for the nitrogen. Each hydrogen has 1. So 1 times 3 is 3. I have 8 valence electrons to work with. So I'll go ahead and put my nitrogen, 3 hydrogens. I'm going to spread them out so the bonding electrons can spread out. And then I have 8 electrons to put in here. So I'm going to put 2 for every bond, 2, 4, 6, 8. Everything's satisfied. Hydrogen likes to be by, or is stable when it's by 2 electrons. Nitrogen's by 8. Then with the SF2. So sulfur, if I look back at periodic table, sulfur has 6 valence electrons, 1, 2, 3, 4, 5, 6. Fluorine has 7, right? It's 1 short of the noble gas. So, in SF2, I'm going to have 6 for this guy, 7 for each of these. So 7 times 2 is 14. Alright, so I'm going to have 20. Alright, I know sulfur is probably going to go in the middle because there's one of those. So I'll put sulfur in the middle. I'm going to put the electrons on. I'll make sure I leave electrons available to bond with the fluorine. So I'll put a fluorine here, and let's start adding electrons. I know I'm going to put a couple for those bonds. And then I'm going to start satisfying things. So how about 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. What I was doing there is I was spreading the electrons out so that if I did have to make a double bond at the end, I would see that, like, well, fluorine has 6 electrons by it, sulfur has 6 electrons by it, I only have 1 more electron pair, so if I needed to make a double bond, it would have been obvious. So if you tend to spread the electrons out as you put them on, so if you just put 2 here, 2 here, 2 here, 2 here, 2 here, so as you go, like, there isn't one atom that has all 8, while other atoms only have 2 or 4. Just try to get everybody with 2, then everybody with 4, everybody with 6, and you'll see if you're going to run out of electrons and need to make a double bond. So there's that guy. Everything's following the octet rule. That's good. Then I have SF4. If sulfur makes 2 bonds and doesn't break the octet rule, I'm pretty sure this one will break the octet rule. I remember this has 6 electrons. Each of these has 7. So 7 times 4, got 28. Okay, I'm going to have 34 electrons. And I know the sulfur is going to be making 4 bonds. So I'll have my sulfur here. For this thing, I'm actually going to go ahead and say, I know sulfur has 6 valence electrons. I'm going to go ahead and put those electrons around the sulfur, leaving 4 of them open for bonding. So it's going to look weird. I've got 1, 2, 3, 4, 5, 6. So those are, I'm going to put that a little closer together. So it's 4 spread out and then 1 pair. Okay, so then the fluorine, I've got 4 fluorines. We go 1, 2, 3, 4. And those 4 fluorines I'm going to be putting on 28 more electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. So I put on 34 electrons total, 6 for these guys, 28 for the fluorines. I can see every fluorine is surrounded by 8 electrons, so it's following the octet rule. The sulfur is breaking the octet rule because it is currently surrounded by 2, 4, 6, 8 bonding electrons and 1 lone pair for a total of 10 electrons. So what the sulfur is doing is it's on the 3rd energy level, it's accessing its Ds. So that is allowed. Let me draw it so we can see what it looks like just a little bit better. 1, 2, 3, 4, and a lone pair. Each of these is a fluorine. You can use lines to represent pairs of electrons. Just don't connect dots, because then it's hard to tell if that's 2 dots in 1 pair or if it's 2 dots that are connected. Okay, so xenon, I know I'm going to break the octet rule. It's going to make 4 valence electrons. So what I'm going to do, I'm going to start with xenon's 8 valence electrons. I'm going to spread them around the xenon, leaving 4 electrons available to bond with these fluorines. So xenon has 8 valence electrons. Let's go ahead and go 1, 2, 3, 4 singles for bonding. And how about 5, 6, 7, 8? So there's xenon's 8 valence electrons. Let me put on the 4 fluorines. 1, 2, 3, 4. And each one of these is bringing 7 electrons. So you can see each fluorine is surrounded by 8. The xenon is breaking the octet rule because it had its own 8 and then it's also sharing these 4. There's 12 by it. But again, xenon, that's all the way down on the 5th energy level, so it definitely has access to Ds for bonding. Next guy, we have this iodide. So I3 minus, iodide is a halogen. It has 7 valence electrons. There's 3 of these guys, so sometimes 3 of them have 21 electrons to work with, plus this -1. So there's 22. I know I'm going to have an iodine in the middle. Let's put one on either side. I guess anything can be in the middle there. So there's going to be 7 electrons here. I'm going to use, or I'm going to leave 2 of those electrons available for bonding. So taking this guy's valence electrons, he has 1, 2, 3, 4, 5, 6, 7. I don't like that I left a random electron there, so that's where I'm going to use that extra 1 electron. I'm going to go ahead and put, it has a -1 charge, so I'm going to say, well, these guys are its valence, that's going to be that extra electron that it gains. So now each of these guys have 7, and you can see it's going to work out. So there's 1, 2, 3, 4, 5, 6, 7. So this iodine is by 7. Same with this one. 1, 2, 3, 4, 5, 6, 7. This guy's by 7. And then this iodine is breaking the octet rule, but it's allowed to because it can access its Ds. Then just to tell people, I did add an extra electron. That was I3 with a 1 minus charge. This means there's an extra electron floating around. One more. PF5. So, phosphorus making 5 bonds. Anything making 5 bonds is breaking the octet rule. This is clearly breaking the octet rule. Phosphorus, if you look on the periodic table, has 5 valence electrons. Okay, I'm going to spread those 5 valence electrons out, leaving them available for bonding, like that. And I'll put a fluorine on each one of those. So here you go. Every fluorine brings 7 valence electrons with it. So here, each fluorine is by 8 valence electrons. So all the fluorines are following the octet rule. That's good because they don't have access to the Ds. They're on the second shell. Phosphorus is breaking the octet rule, and that's okay. It's on the third shell. Has access to those 3 Ds. These get better with practice. Just make sure that you counted your valence electrons and they add up.